The F-35 is not just another fighter jet. It's a multifaceted beast that combines stealth and design. The strongest fighter jet in America's arsenal started off as a bold idea. One jet that could replace many others, fight in the air, and even hover like a helicopter. So how was the F-35 designed to dominate the skies? Let's break it down. In the 1990s, America faced the problem of its aging fleet. The F-16 Fighting Falcon was fast but not stealthy. The FA-18 Hornet could fight from carriers but lacked range. The AV-8B Harrier could hover but was unreliable. And the A-10 Warthog was great at close air support but too slow for modern air combat. The Pentagon wanted one jet that could do it all. Thus, the Joint Strike Fighter program was born. The result would be three versions of the F-35. F-35A, conventional takeoff for the Air Force. F-35B, short takeoff and vertical landing for the Marines. F-35C, carrier variant with larger wings and reinforced landing gear for the Navy. The challenge wasn't just making a new fighter, it was making a single airframe adaptable to three different missions, which was something no one had done before. And at the heart of that vision was one critical component. At the core is the Pratt & Whitney F-135 engine, the most powerful fighter jet engine in service today. It produces 43,000 pounds of thrust, nearly double what powers an F-16. The F-135 is a low bypass turbofan with afterburner. First, a three-stage fan pulls in about 400 pounds of air per second, roughly 180 kilograms per second. Next, a six-stage compressor packs that air to about 30 times normal atmospheric pressure. Fuel is added and burned in the combustor at around 2,000 degrees Celsius. The hot, expanding gas drives the turbines at about 10,000 revolutions per minute, and what's left is accelerated out the nozzle to make thrust. Hit the afterburner, and raw fuel is sprayed directly into the exhaust, igniting in a secondary flame that pushes the F-35 to Mach 1.6. That's not as fast as the F-22 Raptor's Mach 2.25, but the F-35 trades top speed for stealth and versatility. For the F-35B, the engine connects to a lift fan, which is a vertical fan behind the cockpit, powered by a shaft from the engine. It produces 20,000 pounds of thrust downward. At the same time, the main nozzle swivels 90 degrees and small roll ducts balance the jet. Unlike the Harrier, which blasted hot exhaust straight down, the lift fan uses cool air, reducing heat damage to decks and improving stability. Now here's a question for you. How much vertical lift can the lift fan system generate in total? Drop your guesses in the comments and we'll answer this one in the outro. What good is power if you can be seen? That's where stealth engineering comes in. The F-35's shape is designed to scatter radar waves. Its fuselage blends smoothly into the wings with no sharp right angles to reflect radar. It has canted tail fins, the inlets are S-shaped to hide the engine face, and the exhaust nozzle is flattened to reduce radar and heat signatures. The entire jet is coated in radar-absorbing materials. These layers soak up or scatter radar energy. Even the canopy is coated with a thin layer of gold, bouncing radar while letting the pilot see clearly. Weapons are stored internally in bays. Carrying weapons on wings creates radar reflections. So, in stealth mode, the F-35 carries 4 missiles or bombs hidden inside. In beast mode, it can carry 22,000 pounds of weapons externally, but at the cost of stealth. These stealth decisions make the F-35 nearly invisible to radar. In combat exercises, F-35s have scored kill ratios as high as 20-1 against older jets. The F-35 had to be light, tough, and heat-resistant. A near impossible combination. Engineers solved it with advanced materials. 35% of the jet is titanium, forming its backbone and tolerating high heat and stress. 42% is carbon fiber composite, which is lightweight yet incredibly strong. The rest is aluminum and other alloys. Thermal coatings reduce infrared emissions. Even the paint is engineered to resist heat buildup while remaining stealthy. The airframe was also designed for maintainability. Unlike the F-22, whose stealth coating requires long repairs, the F-35's composite skins are easier to replace and maintain. The result is a jet strong enough to withstand carrier landings but light enough to maneuver and stealthy enough to hide. If the F-135 is the jet's heart, the sensors are its brain. The ANAPG-81 Advanced ASA radar can track dozens of targets simultaneously and jam enemy radars. It can even map terrain with incredible precision. The distributed aperture system uses 6 infrared cameras around the jet to give the pilot complete 360-degree coverage. With the F-35 helmet, the pilot can see through the jet, viewing infrared video as if the jet were transparent. The electro-optical targeting system adds laser targeting and infrared search, and is built seamlessly into the nose. All this data is fused by onboard computers and projected into the pilot's helmet display. There's no need to look at multiple gauges. Everything like the radar tracks or threat warnings is presented as a single picture. Older pilots say it's like moving from black and white television to high-definition streaming. The F-35's internal bays hold 2 AIM-120AM RAM missiles and 2 2,000-pound JDAM bombs in stealth mode. Smaller diameter bombs allow even more capacity. Externally, pylons can carry Sidewinders, JSON cruise missiles, and heavy ordnance. The F-35A includes an internal 25mm GAU-22 cannon, firing 3,300 rounds per minute, while the B and C versions use an external pod. This flexibility allows the jet to shift roles instantly. Stealth assassin one day, bomb-laden strike aircraft the next. But no weapon matters without the ability to control the aircraft itself. The F-35 is inherently unstable by design. This instability gives agility, but it requires a fly-by-wire system where computers make constant micro-adjustments to keep it smooth. The jet's software runs millions of lines of code, which is more than any commercial aircraft. It integrates flight controls, radar, sensors, and weapons into one system. For the F-35B, hovering is computer-assisted. The pilot doesn't need to manually balance thrust. With one button, the jet hovers. The system automatically adjusts lift fan, nozzle, and ducts. This engineering choice of using digital control instead of manual complexity made vertical flight practical for everyday pilots, not just specialists. But even the most advanced code needs to be proven in the real world. The F-35 underwent 8,000 flight tests before full production. The Arctic trials proved the engine could restart at -40 degrees Celsius. The desert trials showed it could fly through sandstorms in 50 degrees Celsius heat. They also conducted hover trials, which demonstrated that F-35Bs could transition from hovering to supersonic flight in under 8 seconds. In combat, Israeli F-35s have struck Syrian targets undetected. USA's F-35s have flown missions in Iraq and Afghanistan, integrating seamlessly with older jets. Critics argue about cost and maintenance, but its battlefield performance proves the engineering works. But to really understand what makes the F-35 different, you have to look at where the pilots sit. Step inside the cockpit and you'll notice something unusual. There's no traditional head-up display. For decades, fighter pilots relied on a HUD to project speed, altitude, and even targeting onto the canopy glass. The F-35 throws that out entirely. In its place is the helmet-mounted display system, a $400,000 piece of engineering that turns the pilot's visor into a full panoramic screen. Every piece of information is projected directly onto the helmet. Using the distributed aperture system, the pilot can literally see through the jet, with infrared cameras projecting live video beneath their feet. Wherever the pilot looks, sensors and weapons follow, allowing them to lock and fire simply by aiming their eyes. Each helmet is custom molded to the pilot's head, ensuring the displays are perfectly aligned. This philosophy reduces workload and increases awareness. Instead of juggling dials and scopes, the pilot sees one fused picture of the battlefield. For the F-35, information itself is the ultimate weapon. The F-35 story begins with the X-35 prototype built by Lockheed Martin. The X-32 had a large, ungainly intake and struggled with vertical flight. The X-35, in contrast, successfully demonstrated short takeoff, supersonic dash, and vertical landing in a single flight, and it was the first jet ever to do so. That win secured the Joint Strike Fighter contract. Lockheed Martin partnered with Northrop Grumman and BAE Systems, while Pratt & Whitney built the F-135 engine. The program ballooned to over $1.5 trillion projected lifetime cost due to delays. Yet despite criticism, The F-35 is now the most numerous fifth-generation fighter with over 1,000 delivered. Now let's answer that question from earlier. The lift fan system makes 40,000 pounds of vertical lift, which is enough to raise the 30-ton jet off the ground. The F-35 Lightning II proves that it is more than a fighter jet. It's the most ambitious engineering project in aviation history. At first glance, Concorde's wings look like a simple and elegant sweeping triangle. But these weren't ordinary wings. They carried 100 passengers across the Atlantic at twice the speed of sound, through shock waves and intense heat. To this day, the Concorde wing remains one of the most daring pieces of engineering in aviation history. So how do you design a wing that can take a passenger jet higher and faster than some fighter aircraft? Let's find out. The most distinctive feature of Concorde was its OG delta wings. Most airliners use swept wings with flaps, slats, and spoilers. Fighter jets sometimes use pure deltas. But Concorde's designers at Sud Aviation and British Aircraft Corporation needed something in between for a wing that could cruise at Mach 2 and still land safely on a conventional runway. The delta gave inherent strength and stability at high speeds, but the real trick was in the leading edge. Instead of a straight line, Concorde's wing had a graceful S-shaped curve, the OG. This shape generated controlled vortices as air spilled over the wing. Those vortices created extra suction boosting lift at low speeds when Concorde had no flaps or slats to help. Engineers proved this in years of wind tunnel testing, studying vortex flow with smoke and laser visualization. Variable geometry swing wings were considered, but rejected for their weight and complexity. Concorde's fixed delta was simpler, lighter, and more reliable, and it also took advantage of vortex lift. Test pilots later described it as riding on invisible whirlwinds. At approach speeds of 160 knots, Concorde could still fly safely thanks to this effect. It was a radical idea because passenger jets weren't supposed to behave like fighters. Yet this was the only way to blend subsonic safety with supersonic efficiency. But clever shaping alone couldn't make a supersonic airliner work. The wing needed materials that could withstand the punishing heat of Mach 2. At Mach 2, Concorde's aluminum skin heated to over 127 degrees Celsius, 260 degrees Fahrenheit. Engineers initially considered titanium, which was stronger at high temperature, but rejected it. It was too costly, too heavy, and too difficult to machine for such a large aircraft. Instead, they developed a special alloy known as RR58 aluminum. This was tested exhaustively in temperature chambers, bent and stressed until failure to prove it could hold strength near its upper temperature limit. Even so, engineers knew the structure would expand. In fact, Concorde stretched up to 10 inches during flight. Pilots joked that the cockpit windshield would grow warm to the touch, which was a reminder that the entire jet was expanding around them. This expansion had curious effects. Carpets rippled, cabin fittings shifted, and tiny gaps appeared between panels. Passengers sometimes worried, but the engineers reassured them that these gaps were designed in. When Concorde cooled on the ground, everything shrank back into place. Fatigue management was critical. The repeated expansion and contraction cycle was unlike anything on subsonic jets. Engineers scheduled frequent ultrasonic inspections of the wing structure to catch microscopic cracks early. Maintenance was as much a part of the design as the alloy itself. At Mach 2, Concorde's wings were doing something else most people never realized. Beyond lift and balance, the wings carried a hidden advantage that set Concorde apart from every other jet of its time. What do you think this was? Drop your guesses in the comments below and we'll reveal it in the outro. With materials sorted, engineers started wondering how to make wings and engines work together at supersonic speed. Concorde's 4 Rolls-Royce Snecma Olympus 593 turbojets were powerful, but they couldn't run at Mach 2 on their own. The secret was in the wing engine integration. Each engine sat in a complex nacelle under the wing, with variable intakes controlled by ramps and auxiliary doors. At supersonic speeds, air slams into the aircraft too fast for engines to use. So the intake slowed the airflow from Mach 2 to subsonic before feeding it into the compressors. Sensors monitored pressure every millisecond. Hydraulic actuators moved the ramps in tiny increments, trimming the shockwave at the intake lip. Pilots could hear the system at work as a metallic hum while the ramps adjusted. If it failed, the engine could unstart, violently coughing out flames and thrust. Here's where the delta wing came in. Its shape guided shock waves perfectly into those intakes, stabilizing them. Engineers called this wave riding. If the shock wave shifted, the engine would surge. But with the wing and intake tuned together, Concorde achieved a remarkable level of stability. The result was an aircraft that cruised at Mach 2 for hours without surging or stalling, a supersonic airliner that could reliably cross the Atlantic in under 3.5 hours. The intakes and wings gave Concorde speed, but slowing it down for landing required an entirely different approach. Concorde's wings had no conventional flaps. Instead, the trailing edge carried elevons, which were control surfaces that combined the functions of elevators and ailerons. At low speeds, the elevons drooped downward, adding camber and helping generate lift. In cruise, they trimmed the aircraft precisely, keeping it stable as fuel shifted and air thinned. The wide delta trailing edge provided the space needed for these multi-role surfaces. Each elevon was powered by redundant hydraulic systems, or 3 separate circuits, so a failure in one wouldn't compromise control. This redundancy was essential for safety at Mach 2, where even small control failures could be catastrophic. Pilots reported that Concorde felt almost fighter-like. The controls were direct with little lag. At Mach 2, even small movements translated to powerful responses. At low speed, the drooped elevons kept the jet controllable. Another trick was the drooped nose, which was not part of the wing itself, but essential for wing use. On approach, pilots needed to see the runway over that long delta. The nose hinged downward, and the transparent visor retracted, improving visibility during landing and takeoff. Form followed function in practically every sense. But even with elevons and a droop nose, the real enemy of supersonic flight was invisible. At Mach 2, Concorde had to battle wave drag. Shock waves formed along the leading edge, and if they detached, efficiency collapsed. The OG curve helped hold those shock waves in place. The thinness of the wing also mattered. At just 3% thickness-to-chord ratio, Concorde's wing was razor slim. That minimized drag, but demanded extraordinary precision in manufacturing. Panels were milled to tolerances of fractions of a millimeter. Even insect residue on the leading edge could disrupt the flow and raise drag. That's why Concorde's skin was polished to a mirror finish. It wasn't vanity, it was necessity. A smooth surface ensured predictable shock waves and minimal drag. Engineers even worried about layers of paint adding roughness and weight. The payoff was astonishing. Concorde achieved a lift-to-drag ratio of 7.5 at Mach 2, which was far better than earlier supersonic concepts, and the key to its viable transatlantic range. But Concorde's most ingenious use of its wings wasn't just aerodynamic. It was hidden inside. Concorde's delta wings doubled as giant fuel tanks. Together with fuselage tanks, they carried over 96 tons of jet fuel. But this wasn't just about storage. The fuel inside was part of Concorde's balance system. At subsonic speeds, the aircraft's center of gravity sat forward. As speed increased through Mach 1, shock waves moved lift rearward. To counter that, Concorde pumped fuel from forward tanks into aft tanks inside the wings and fuselage. At Mach 2 cruise, much of the fuel sat near the tail. Instead of trimming with control surfaces which would add drag, Concorde used fuel as ballast. 11 pumps constantly moved fuel during flight, guided by the flight engineer at his console. He watched gauges showing the levels in 13 different tanks, shifting kerosene like a liquid weight system. Passengers never saw it, but every Concorde crossing was a constant ballet of fuel, moving inside the wings to keep balance perfect. It was a perfect example of engineering turning a necessity into a solution. Then engineers worked on fuel leaks due to intense heat in the sky. On the ground, Concorde often appeared to be leaking fuel. Dark streaks ran under its wings. To many, it looked like a fault, but it was intentional. Because Concorde's aluminum expanded during flight, the tanks couldn't be sealed tight on the ground. Small gaps were left to allow for that stretch. At Mach 2, when the whole jet heated and expanded, the gaps closed and the tanks sealed. The leaks stopped at the exact moment Concorde reached supersonic cruise. Passengers sometimes asked why their luxury jet dripped fuel at the gate. Engineers explained it calmly. Only at twice the speed of sound was Concorde truly airtight. What looked like a flaw was actually proof the design was working. Maintenance crews became experts in monitoring these expansion gaps. Regular inspections ensured the deliberate imperfection never became a weakness. It was another example of Concorde's unique design philosophy of accepting quirks that subsonic airliners never faced. With these challenges mastered, Concorde's wings became more than structure. They became a symbol of daring engineering. Even after Concorde's retirement in 2003, its wing remains legendary. It proved that a civilian aircraft could use advanced aerodynamic tricks once reserved for fighters. The OG Delta influenced later supersonic studies like NASA's high-speed civil transport and today's boom supersonic overture. NASA's X-59 Quest project borrows heavily from Concorde's lessons, exploring thin airfoils and vortex lift for quieter supersonic flight. In wind tunnels today, researchers still analyze Concorde's OG curve as a benchmark. And beyond technology, the Concorde wing stands as a symbol. It wasn't the cheapest solution, it wasn't the easiest, but it worked by carrying passengers at Mach 2 for 27 years. In that time, Concorde flew 50,000 plus supersonic flights. Everyone depended on the brilliance of its wings. So what was that hidden strength of Concorde's wings? It was their sheer durability. Despite flying faster and hotter than any passenger jet before or since, Concorde's wings never suffered a single catastrophic structural failure in 27 years of service. The OG Delta wasn't just elegant or efficient, it was absolutely resilient. If you enjoyed this breakdown, don't forget to like, subscribe, and share for more deep dives into aviation's greatest engineering feats.